This conference will now be recorded.
Okay, so today's topic is about vectors and vector equations. You will see that everything is related to the matrices and the system of linear equations. Okay, uh, linear, as I said before, linear algebra is all about system of linear equations. So, uh, if you simply look at the vectors, we called it column matrix as well, right? When we have just one column and more than one rows, right? So basically anything like this, number of rows, but there is only one column. So m by 1 matrix basically. For example, these are 2 by 1, right? 2 rows, 1 column. These are all 2 by 1. Column is only 1. So these are usually written as vectors. Okay, column vector or simply a vector. Sometimes we define row vectors as well. For example, there is just one row and more than one column, right? So if we are playing with both of them, then we use the terminology row vectors and column vectors. But when we are simply using the same notation as one column, then we can simply call it a column, simply a vector instead of saying column vector. So any number of entries, okay, written in one column. There can be 2 entries, 3 entries, 4 entries, any number of entries will be a vector. But that will be a vector in different sets. Okay. So if we pick any two real numbers, and write them as one column, right? It will be a vector in R2. R2 is a space R by R, right? It's a two-dimensional space. We call it two-dimensional space. So one value from here and one value from here. Okay. So if you pick this point and join it from the origin, this is basically a vector which is written here. Okay. So any vector in R2, so this space, set of all vectors, you see, if I pick any vector here, any vector, all these vectors give me R2, space of R2. Simply R is a set of real numbers. Set of real numbers means just one line. Set of real numbers somewhere here, somewhere here, somewhere, right? All the points on this line are the set of real numbers. Now we have two real lines. One is vertical, one is horizontal. Two real lines. Now all the points, all the vectors here will be set R square. So R square contains 2 by 1 matrices, all 2 by 1 matrices, where these entries are from real numbers. These are real numbers. So if you pick any two vectors, u and v, they can be anywhere, right? They can be 1 2 3 4, -2 1 5 7, any two vectors from R square. Then these two vectors will be equal if the first one is equal to the first one and the second one is equal to the second. If these u1 is equal to v1 and u2 is equal to v2, then they will be equal. Remember, if you have a vector 1 2 and if you have a vector 2 1, they are not equal. You see, they both have the same thing, 1 2 and 2 1, but they are not equal. Why? Because first is not equal to the first one and second is not equal to the second one. So arrangement is very important here. So 1 2 is only equal to 1 2. That's it. Okay. Similarly, if you are adding these two vectors, you can add the first one into the first one and second into the second one. You know, these are basically 2 by 1 matrices. So we can treat them as 2 by 1 matrix. A vector can be treated as m by 1 matrix as well. So all the results from matrices will carry to the vectors as well. Okay. So Cu, if you are multiplying a constant with a vector, it means you have to multiply this constant with both of them. C will be multiplied by u1, C will be multiplied by u1, u2, okay, for any constant. So how can we interpret them geometrically? How can we see them geometrically? So this is the description of any vector. You know that if you have a point uv, then what you do? You go u1, u distance in x direction and v distance in y direction, right? If you go in u direction, u distance, and you go v units in y direction, then you reach to this point uv. This is the point uv. But if you make a straight line from the origin to this UV with an arrow, because you are pointing outside, okay, it's a vector. Vector has the length as well as the direction. So this vector, this line is basically the vector UV. Okay, for example, if you want to see where is 1 3 3 1, so what I will do, I will go 1 2 3 units here and 1 unit in this direction, right? So this is the point 31. This is the point 31 on XY axis. But if I join from the origin to 31, it's a straight line. I'm using the mouse, so that's why it's a vector, straight line vector. This is the vector 1 3. Sorry, 3 1. This is the vector 3 1. Okay, and if you want to make a vector 1 3, 1 3 1 3 will be 1 in X direction and 3 in Y direction. So 1 here and 3 here, you see. So this is the vector. If I go to this is the vector 1 3. So you see 1 3 and 3 1 are different vectors, right? So these are the geometric description of vectors. Got it? So if I add two vectors, where do they go? If you have a vector u, this is a vector u up till here, and this is a vector v up till here. These are two vectors. You can complete a parallelogram. What is a parallelogram? You draw a line parallel to u. So this is a line parallel to u, right? And this is a line parallel to v. You see, parallel to v. You complete a parallelogram. Now this diagonal, this is called the diagonal of the parallelogram. This diagonal is the sum of these two vectors. Got it? So whenever you add these two vectors, you will get this diagonal. Okay. So here, uh, for example, this was 3 1 and this was 1 3. So if I complete this parallelogram, this vector, this diagonal, this vector will be 4 4. This vector will become 4 4, because if you add these two, 3 plus 1 and 1 plus 3 becomes 4 4, and this is, see, exactly the diagonal of the parallelogram, because this point becomes 4 here and this point becomes 4 here. You see, exactly, this is 4 4, which comes from the sum of these two vectors 3 1 and 1. Okay, so this is called the parallelogram rule for addition. Parallelogram rule for addition. Let me check if there are any questions. Okay. Similarly, if you have three entries in the vector, if you have still one column, but now there are three rows, it means there are three entries from the real line, three real numbers arranged in one column, then these will be the vectors in R3. They will be the vectors from R3, because now you have three dimensions. Now one is coming from this line, let's say u from here, v from here, u1 from here, u2 from here, and u3 from the third axis, which is your z axis. Okay, so this is somewhere in the space, u1, then in u2, then in u3. This is your point u1, u2, u3. So if you join them, this is the vector, this is that vector u1, u2. This is not on the paper. Now this is in space, somewhere in the space, because three dimensions are not on a paper. Okay, you are in a three-dimensional place where you are sitting. Your head, just look at your head. Head is a point in a space. It's not on floor, it's not on the wall, right? You are outside of the wall, outside of the floor. So this vectors will be somewhere in the space, coming from the origin, going outwards to the point you want to use. Okay, so if I select all the points like this, that will be my set or R cube, three-dimensional space. So similarly, I can carry on and go to any dimensional space or n. It means by taking just one column, if I arrange any number of elements, 1 2 3 4 5 6 up to 10, it can 10, 20, 30, whatever, that will be called n-dimensional space or n-dimensional set or n. Okay, what is Rn? Rn is a vector which has n entries. Simple definition is that Rn has is a set of vectors who have n entries in it. R3 is a set of vector which has 3 entries in it. R2 is a set of vector which has 2 entries in it, right? So this power only gives you the number of entries in the vector. Got it? So there are some properties comes from the matrices as well. You can add two vectors u plus v plus u, they will remain the same. U plus v plus w and u plus v plus w means you can change the order of operation, it will remain the same. 0 is a vector which is called, if you add 0 in any vector, that vector will not change. Why? Because all entries of 0 vectors are 0. We call it a 0 vector. Similarly, a negative of the vector, if you add u and negative u, it gives you 0, right? So where is the negative vector base? Basically, if you have this vector u, this is your vector u going in this direction, right? Then negative of u will be exactly on the opposite side with same length. Same length, opposite side gives you minus 2. Okay. So if the right side is u, only the direction is changed. Direction is opposite now. Okay. Length will be same. U and minus u have the same length. Only direction is opposite, exactly opposite. If you are multiplying c with u plus v, you can multiply c with u and c with v and add. Right? Simple rules of multiplication. Okay. One thing which is very important in linear algebra is called linear combination. What we mean by linear combination? If you have some number of vectors, let's say p vectors, v1 up to vp, they can be 2, 3, 4, 10, 15 vectors, whatever, finite number of vectors, right? And some real numbers, some scalars, c1, c2 up to cp, same number of real numbers. Okay. So if you write this type of thing, you are multiplying one constant with one vector, second constant with second vector, third constant with third vector, and keep adding. Okay. This type of expression is called linear combination of the vectors, not of scalars. We introduce scalar on our own. This is called the linear combination of vectors v1, v2, v3 up to vp. Okay, so this is a new vector. We can call it y. It's another vector. Okay, so linear combination of a vector is also a vector, and these constants c1, c2 are called weights because you can change the weights. For example, you can write 2v1 plus 3v2. This is a linear combination of v1 and v2. You can have another vector v3. This is a linear combination of v1, v2, v3. And what are the weights here? Weights are 2, 3, and minus 1. These are called the weights. You can change these weights as well. That will be a new linear combination. For example, v1 plus v2 plus v3. Now all weights are 1. 1v1 plus 1v2 plus 1v3. All weights are 1. C1, C2, C3 are 1. This is another linear combination of v1, v2, v3. Okay, so you can make linear combinations of any vectors. That's not an issue, right? So the problem is, sometimes the question is, can we write a given vector as a linear combination of two vectors? Let's say this is a question. A question is, a1 and a2 are given vectors, and another b is a third vector. The question is, determine whether b, this vector b, can be written as a linear combination of a1 and a2. What does that mean? It means, can we write b as a linear combination of a1 and a2? What is a linear combination? Multiply some number with a1 plus multiply another number with a2, and the answer should be equal to b. But I don't know what will be those numbers a1 and a2, right? We are not sure what are these numbers. C1 and C2. C1 and C2 are similar, but it's very difficult to write C1 and C2. How to guess whether B1 will be what constant time A1 plus another constant time A2? Basically, this is the question. Can we write it like this or not? Are there any C1 and C2 or not? So I made it a question. We said, okay, I don't know whether there will be a C1 or C2 or not. So we said, because these are unknown, and we usually write unknowns as x1, x2. X1, x2 are the variables which are not known to me, right? So I made a question like this. I said, okay, let's multiply x1 with a1 and x2 with a2 and put it equal to b. If we can find this x1 and x2, then my answer will be yes, right? Yes, I can write in terms of a1 and 2. If I cannot find x1, x2, then my answer will be no. That no, I cannot find, I cannot write b as a linear combination. Understand? So if I multiply, this is a constant x1 and this is a vector. How we multiply? We multiply constant with every value of the vector. Similarly, this x2 will get multiplied with every value of the vector. So this becomes x1 minus 2x1 minus 5x2. So I got x1 minus 2x1 minus 5x2. Similarly, this x2 will multiply by 2, 5, 6, becomes 2x2, 5x, 6x2 equal to. Now, if I add these two vectors, then x1 plus 2 should be equal to 7. So I got x1 plus 2x2 should be equal to 7. 2x1 plus 5x2 should be equal to 4. And 5x1 plus 6x2 should be equal to minus 3. So I got these three equations. And you see, what is this? This is a system of linear equations which we have studied before. I know this is a system of three linear equations, and I also know how to solve it. So you see, totally different question. Totally different question. You are seeing this question for the first time. Determine whether a given vector B can be written as a linear combination of given vectors A1, A2. But you see, when we are going to solve it, we got a linear system to solve, which I already know. So this is a system of three linear equations in two unknowns, x1 and x2. So how we solve it? We write the augmented matrix. We write 1, 2, 7, minus 2, 5, 4, minus 5, 6, minus 3. This is the augmented matrix. And then we reduce it to echelon form or reduced echelon form. What we do? This is my pivot element. I will use this pivot element. I will use this pivot element to make these two things minus 2 and minus 5 0. So what I will do, R2 plus 2 R1 and R5 plus 5 R1. You will not get this step unless you practice these row operations. If you do not practice the row operations, it will remain very hard question. Okay, with a little practice of row operations, you can make it very easy. So so R2 plus 2 R1 means you multiplied first row with 2 and added in the second one. So first row is not changed. We are only using the first row. You see, the first row is only being used. So first row will remain 1, 2, 7. Minus 2 plus 2 will become 0. 5 plus 4 will become 9 because 2 into 2 is 4 plus 5 is 9. You see, 5 plus 2 will become 9. 4 plus 14 because 7 times 2 is 14 plus 4 becomes 18. So you see, you got 0, 9, 18 as your row 2 because row 2 is changed here. Now for row 3, I multiply this by 5. 5 minus 5 gives you 0. 10 plus 6 gives you 16. And 7 5s are 35 minus 3 is 32. So you see, you got this. Right? Now I got both zeros underneath. Now I want 1 here. I want 1 here now, right? This is my next pivot element. This is my next pivot element. So this should be converted to 1. Then I will make this 0 and this 0, right? This is the pivot position. So what I can do, I can divide the second row by 9. So if I divide the second row by 9, I will get 0 and 2, right? So this is my new row from here. This is my new row. Now I got the pivot element here. I got pivot here, so I can make above and below 0. How I can make above and below 0? I can multiply this by 2. I can multiply this by 2 and subtract from here. So minus 2 plus 2 will be 0. And I can multiply this by 16 and subtract from here. So this will also become 0. So now I am using row 2 to make R1 and R2 0. So you see, minus 2R1 minus 2R2, sorry, this is not R1, this is 2R2. This is also 2R2. Just fix this in your notes. This is 2R2. Now we are using R2 to make the 0. So minus 16 R2 in R3 and 2R2 in R1. So 2R2 in R1 will make this 0 and 16 R2 in R3 makes this 0. Right? So I got 0 and 0 here. But how the other things will change? This is 0. And minus 2 times 2 is minus 4 plus 7. Minus 4 plus 7 gives you 3. Minus 16 plus 16 gives you 0 here. And 16 twos are 32. Minus 32 plus 32 is again 0 here. So the whole row becomes 0, no problem. Whole row becomes 0, no problem. Why? Because the third row gives you 0 equal to 0. So I still have a solution here. You have 0 equal to 0. So no problem. This is fine. 0 can be equal to 0. Okay. If you have some number here at the end, if this is not 0, if this is 1 or something, then you have 0 equal to 1. So no solution. Always remember. Okay. If you have 0, 1, 0, still you have a solution because this gives you x2 and equal to this gives you 0. No problem. X2 0 is still fine. So only problem comes when you have 0, 0, 0, 0, all zeros, and at the end you get a non-zero thing. Because this gives you 0 equal to 1, which is not true. Okay, always remember. So this is fine. 0, 0, 0, not a problem. If I give you a question of finding the rank, what you will do? You will say that because this is the echelon form of the matrix and there are two non-zero rows here. So two non-zero rows gives you the rank of the matrix. So rank will be 2, but question is not the rank. बना लो उमर उसको बना दो पिक्चर्स बना के मुझे बुला लेना. All right, so we got, now this is the row reduction. So from here your x1 becomes 3 and x2 becomes 2 because it's the organic matrix. First two rows are for x1, x2 and the last on the right hand side. So x1 becomes 3 and x2 becomes 2. Got it? So that is your solution. So this is, we used, what method we used here to solve this system? This method is called Gauss-Jordan method. When you reduce your matrix to reduced echelon form means above and below both are 0. Here I don't need to make it 0. Why? Because there is no pivot here. We only look at the pivot element and make zeros above and below. Got it? So it means you got the solution. You got x1 and x2. So x1 is 3, x2 is 2. It means I got the answer here. I got x2 is equal to 3 and x2 is equal to 2. So my B can be written as 3a1 plus 2a2. B can be written as 3a1 plus 2a2. Hence, B can be written as a linear combination. So the answer to my question is yes. The answer to my question is yes. And I can give you the answer as well. Yes, with the weights 3 and 2. With the weights 3 and 2, we can easily write our solution. Okay. Any questions so far? If that is okay, I'll move forward. All right. So see, system of equations related to the linear combination of vectors. Okay. So again, if you know the concept, if I ask you the same question that determine whether B is in can be written as a linear combination of given vectors, basically you have to solve a system of linear equations. Okay. So you see, if you look at original, uh, if you look at the original question, the question was whether B can be written as a linear combination of A1 and A2, right? So can we find some number C1 with A1 and plus C2 with A2 so that this linear combination is equal to your B, right? These set of all these equations, let's say if I keep writing, if I don't say that this is B or not, just forget about this. Just look at this linear combination of A1 and A2. Okay. So if let's say 2A1 plus 3A2, this is one linear combination. I'm not asking you whether this is equal to some vector or not. I'm just writing a linear combination of A1 and A2. Another linear combination is A1 minus A2, right? Another linear combination is 3A1 minus 7A2. You agree with that? All are linear combination. Even A1, 7A1, this is also a linear combination. Why? Because you can write it as 0A2, 7 and 0, just 7A1. So even if I just write A1 or any point into A2, these are all linear combination. So if I write the set of two vectors A1, A2, linear combination, if I write all the linear combinations of A1 and A2, all linear combinations of A1 and A2 are fixed here, right? What we are doing, we are writing different C1 and C2 for C1 and C2 from the real numbers. So what we will call this set? This is the set of all linear combinations of A1 and A2. Set of all linear combination of A1 A2. We have a name for that. We call it a span. We call it a span of U1, A1 and A2. Span of A1, A2, A1 comma A2. If I give you any vectors and ask you what is the span of A1 and A2, that is the set of all linear combinations of A1 and A2. If I give you three vectors A1, A2, A3, then the linear combinations of all those three vectors will be a span, right? So this is what we call, this is a set is spanned by U1 and U2 or generated by U1 and U2. A set generated by U1 and U2. So these all are the terms which are used. Set spanned by or generated by, because A1, A2 generated this set. Okay. Set generated by the vectors A1 and A2. C1, C2 are changing numbers. Set generated by A1, A2, or we also call it spanned by. That's why we call it span. Spanned by A1 and A2. And or generated by A1 and A2. Okay, this is a theory I wrote here. A set generated by A1 and A2 or spanned by A1 and A2. Okay, so these all are your see spanned or generated. Okay, so this is the set which contains the set of all vectors that can be written in the form of linear combinations. These are just the names related to the related to this theory. Okay, so how geometrically I can see if you are writing a span of V. What is a span of V? Span of V is a set which is generated by only one vector v. So it means I can keep multiplying. I can keep multiplying numbers with this vector CV because there is only one vector, so just CV. So if you multiply, if this is your v from here to here, if this is your v from here to here, then if I multiply 2, it becomes double in the same direction. This becomes 2v. Okay, this becomes 2v. If I go to the opposite side, it becomes minus v. If I go opposite side and double the length, it becomes minus 2v. Right? So same vector extending, extending. If I make it half of it, if I make it half of it, it becomes 1/2 of v. That can also be the c, right? C can be 1/2 as well. So half is the 1/2 of the length. So all the vectors, this span is only this straight line extended towards infinity from both sides. It becomes the line. Okay. But if you have two vectors, let's say span of u and v, if one vector is u and one vector is v, right? Then the span will be the plane which is built by all these vectors in both the directions, in u directions and in directions. So all these vectors, because I am getting two u1 in u1 direction and one in v1 direction. So this will become, this law of parallelogram says that this is 2u1 plus v. This is 2v plus u. This is 4v plus u, right? So if you keep on adding u and v, you get all these vectors here in the plane. So this becomes a plane through the origin, span of u1. Span of v is a line through origin in the direction of v. Plane through origin in the direction of u and v both gives you the u. Okay, so these are called your spanning sets. Spanning sets spanned from or generated from u one vector or uv two vectors. Okay, so this is the geometry of what we did before. And as we discussed already, the any system can be written as a matrix form as well. This is what we have already done, right? If a matrix A is given and vector X is given, there are two ways of finding the product of matrix with a vector. One form which you already know, that we can take this first and multiply with column, right? So what you will get 2x1, see x1, then plus 3x2, 3x2, right? And plus 4x3. So this is plus 4x. So you can multiply first row with a column, right? And you get this first number. This is the direct computation, right? Similarly, you can pick the second row, multiply by this column, and you will get minus 1x1 plus 5x2 minus 3x3. So you see here, you got the second entry. And similarly, the third one, right? Similarly, the third one. So this is the direct computation of the matrix, which you already know. Another way of writing is this. You can pick the first element here and multiply by the first column here. You again get the same thing, because you see, what is the first thing here? Here, this is x1 multiplied by first column. You see, the first column, 2 minus 1, 6. 2 minus 1, 6. Right? 2 minus 1, 6. So you can multiply x with one column, x2 with second column, and x3 with third column. And then add, you get exactly the same thing. Okay? So either you multiply it directly, you get the same right hand side, or you can multiply these three real numbers, x1, x2, x3 are three real numbers, and multiply the columns to get the right hand side. Okay, so it means your system has three forms, right? Your system has three forms. Let me write it at the end somewhere here. Your system has three forms: a x equal to b, right? Or I can pick the values of x and multiply by the columns of a, x1 a1, plus x2 a2 plus so on, no matter how many variables are there, right? Keep on going. If we have n vectors, I will stop at n. In previous example, we had only 3 vectors. So I stopped at 3 equal to b. It is exactly the same thing. And or I can write the system. The system a1, 1, x1 plus a1, 2, x2 and so on equal to b1. So there are n equations, 1, 2, 3, so on. We can write the system as well, right? So this is the matrix form of the same system. This is the vector form of the same system, and this is the exact actual linear system. Okay, so we can write in any form, and solving means doing the same thing. Okay, so I will just do 2 examples which are very straightforward, simple examples, which are from the, let me okay, no questions. So let me go to these 2 applications. Page 58. I have opened the book here as well. I can go to page 58. I will read the question and then we'll come back here. Example 1, homogeneous system in economics. I think the addition is different, so maybe this is the example on page 49. Page is different, section is the same, page 49. Okay, I can change it here. This is page 49. Maybe the addition is different now with me. Maybe it's the latest edition with page 49. Let's read this example. This is the application of linear system from economics, where we can use this linear system. Okay. Suppose an economy consists of the coal, electric, and steel sectors. There are many countries have different things. For example, Oman has a big economy depending on the oil, right, which you get the oil. Similarly, many people produce electricity, so they sell electricity to earn money. Similarly, some countries have coal and they make electricity from the coal as well. Okay, so these are 3 different things where you can earn money. A country can earn money: coal, electric, which is power, of course, and the steel which they produce, right? Output of the each sector is distributed among various sectors as shown in table 1. Okay, so this is the table 1 which is given. So sometimes what happens is a country is making money from all 3 sectors, but he does not give money directly to the sectors because the government keeps the money and then they distribute it among different places, right? So he said the distribution of the output from coal, it goes to all 3 sectors. It goes to coal as well, it goes to electric as well, and it goes to steel as well. You see, coal, electric, and steel. Similarly, the money which you earned from electricity, 0.4 means 40% goes to the coal, 1% goes to electric, and 50% goes to the steel. So you see, it is 100%. If you add the column, it is 100%. 0.4, 0.1, 0.5 is 100%. 0.6, 0.4 is again 100%. Similarly, 0.6, 0.2, 0.2 is again 100%. So this table is given to you and we have to just read it and make a system out of it. So he said, okay, in second column, for instance, let's say this is the second column. I have already told you that, but let's read it. Second column says that the output of the electric sector is divided into coal, steel, and electric. He said output from the electric sector divided 40% to the coal, 10% to the electric, and 50% to the steel. That's how you are distributing the output from electric to all 3 sectors. Similarly, you can distributing output from the steel to all three sectors, 60%, 20%, and 20% to coal, electric, and steel. Got it? So now, how to make a system of equations from here? So he said, donate the prices of the total annual outputs of coal, electric, and steel as PC, PE, and PS. PC means prices from coal, prices from electric, and prices from steel. S for steel, E for electric, and C for coal. So these are the three variables now. I can call it X1, X2, X3 as well. We can call it X1, X2, X3 as well. But instead of that, we are sticking with the name P for prices, E for electric, C for coal, and S for steel. To do that, then your first row means 40% of PE because it is from P electric, right? 40% from, we have PC for this, PE for this, and PS for steel, right? So it means I should get 0% from PC, so no PC from here, plus 4%, 0.4 from PE, and plus, if we add, and plus 0.6 from PS should go to the coal. And what is coal? Coal is PC, right? So this first row gives me an equation which says that 0.4 PE plus 0.6 PS is equal to 1 PC. See, 0.4 PE plus 0.6 PS is equal to 1 PC. Got it? Similarly, from the second and the third row, we got the equations. 0.6 PC plus 0.1 PE plus 0.2 PS is equal to PE, and similarly the third one. So we got all three. So you see, if I rewrite them, because PE and PE is on both sides, PS and PS is on both sides, so we can bring it on one side and write the answer. So if I bring it on one side, I got this system of equations. So this is a system of equations in three unknowns, PC, PE, and PS. And this is a homogeneous system. Why we call it homogeneous? Because the right hand side is 0. When the right hand side is 0, we call it homogeneous system. Okay? Homogeneous system. That's the reason we wrote homogeneous system here. You see? A homogeneous system in economics. So I got this system, and now how to solve it? We can make augmented matrix and find the solution of that. Okay, there is definitely a zero solution, because you see, if I write a matrix form, it becomes AX equal to 0. So if A inverse exists, then X will be equal to A inverse 0, and A inverse 0 is equal to 0. It means I will get only 0 solution. If A inverse exists, I will only get a 0 solution, which is called trivial solution. 0 is the trivial, because I know that if it is the homogeneous solution, 0 is always a solution. This is a trivial thing, that 0 will always be a solution. I'm not interested in the trivial solution. We are interested in non-trivial solution. So if we solve it, you see the one row becomes 0 here. The third row becomes 0. It means I'm getting a free variable here. So how we can write? We can write the first one as PC plus minus 0.94 PS is equal to 0, right? Equal to 0. So it means I can bring it to the right side. So PC becomes 0.94 PS. Second equation gives me PA. PA minus PE minus 0.56 PS equal to 0. So if I bring it to the other side, minus becomes plus. If I bring it to the other side, it becomes point. So see, PS is free here. I did not get any value for PS because third row becomes 0. So it means PS is free. So I did not get only zero solution. I got infinite many solution. It means if PS is 1, then this becomes 0.94 and this becomes 0.56. If PS is 100, then this becomes 94 and 56, right? So for example, if I take PS is equal to 100, right? Then PC becomes 94 and PE becomes, so there are infinite many solutions, not just 1 or 2 or 3 solutions. So so it means the inverse of A does not exist here. If inverse of A exists, then x equal to 0 is the only solution. But you see that A inverse does not exist and we still have a solution, right? There was a true false in midterm as well. I said if A inverse does not exist, then there is no solution of the system. Many people said it is true. It is not true because system can still have a solution. Okay. If A inverse does not exist, it means we cannot use inverse method. This is what we mean. If A inverse does not exist, we have to use row reduction, Gauss-Jordan method to find the solution. There may still be a solution. So similarly, another example given from this is the network flow. This is a network of cars. You see the two roads are going. These are the roads, one-way roads. And it says that the flow of the cars is given. So we call it a network flow because this is a network of roads and flow of the cars. So this is called the network flow problem. Network flow problem. Okay. So what is happening from each intersection? Some cars are coming in at the intersection at the roundabout, and some cars are going out. This is some network in Baltimore streets. Baltimore is a city in Maryland. Maryland is a state in America. In American state of Maryland, there is a city Baltimore, a very nice city. I have visited Baltimore during my PhD. Very, very nice. This is a sea. So if you go here, these are the intersections. So it means at every intersection, there is some flow coming in and going out. For example, in this, this is A, right? This is A. At A, 300 car are coming in from here, 500 coming in from here. So it means total coming in are 800, right? Total coming in are 800. 5 plus 3, 8. And going out are x1 and x2. I don't know how many go in this direction and how many go in this direction, but we know x1 and x2 are going in opposite direction. So it, you know, no car stays at the roundabout. Agree with that? No car stays at the roundabout. Every car which is coming into the intersection has to go out from there. That's why outflow should be equal to inflow. So this is the inflow and this is the outflow, must be equal to each other. So see, I got a linear equation here. Similarly, this is the linear equation from A. I can find linear equation from B, from C, and from D. So I will get 4 equations. But you have to see that how much is the total inflow and outflow. So you see total inflow is 100 plus 400, 500 plus 500, 1000 plus 300, 1300 inward flow. What is the outward flow? 300, 600, 900 plus x3. So x3 is not given to me. It means another equation comes from the overall flow, right? So there will be 5 equations altogether, 4 from the intersections and 1 from outside because x3 is not known to us. So 1300 are coming in, 900 are going out with x3. So 900 plus x3 is equal to 300. So you see these are all our 4 equations from the intersections, flow in and flow out, and 1 at the end which gives me the overall flow of the system. Got it? So overall flow from the system is this one. 900 plus x3 is equal to 1300. So 13 minus 9 gives you 4. So you see again, I got a system of equations, 5 equations in 5 unknowns, but it is not a homogeneous system now. Why not homogeneous? Because right hand side is not 0. So this is a non-homogeneous system, right? So you may have a unique solution, or you may have infinite many solution, or you may not have any solution. We don't know. But we have to write the augmented matrix. You have to write the augmented matrix, row, reduce it to echelon form, and then solve the system. So they reduce it. You see the row reduction algorithm, they skip it. So you have to write the augmented matrix and reduce it to reduce echelon form, and from there they wrote this system. And again, X5 is free here, so you got infinite many solutions, not just one solution. So still you see X1, X2, X3, X4 are written in terms of 5, and X5 is free. So it means again you have infinite many solutions, because you know that a system may have no solution, a unique solution, or infinite many solutions. So there are infinite many solutions. So these are two examples of the linear system from the real world. You see, sometimes we wonder or we ask questions that why we are studying linear system, why we are studying linear algebra, where we can use it. Okay, so there are many applications where you deal with the system of linear equations, and if you do not know anything about linear systems, you cannot proceed, right? So knowing linear algebra is very important, and it has a lot of applications in engineering and other fields. Okay, so I'm stopping here today's lecture. So this was all about linear systems and everything. We got two applications of that as well. Next time I will go back to determinants. We studied determinants and we studied one method of solving determinant. Next time I will use row reduction algorithm to calculate determinants, and there is a Cramer's rule to solve the linear system. So we will solve a linear system using determinants, which is known as the Cramer's rule. So next time I will come up with determinants again and a new method which is called Cramer's rule. So up till then, bye from me. So